Okay, so this is working for everybody?
It's working for me.
Okay, great. So yeah, so I wanted to talk about what the title says, that the class of congruence semidistributive varieties is not definable with a strong Maltsev condition. So there's three basic parts of the talk. The first, I just want to go over some basic definitions. And the second, I want to talk about the connection between the SD-meat condition and the commutator that's been known for quite a while. And then in the third part, we'll discuss how to prove that a particular Maltsev condition that comes out of the commutator can be used to show that this is not strong. Um, and yeah, so let's get into it. Um, So if I have two varieties, the first one is the model of some equations, and the second one is the model of some other equations, and the respective signatures are tau 1 and tau 2, then an interpretation of the first variety into the second variety, well, it's just a way of replacing in the identities in sigma 1 some tau 2 terms so that the identities hold in the second variety. Uh, And there's many ways that people like to talk about this. I think one of the cleanest and most elegant is that variety one interprets in variety two if there's a clone homomorphism from the clone of variety one into the clone of variety two. So what we're really looking at is a preorder on the class of varieties, or if you prefer, the class of clones. And we write V1 less than or equal to V2 to indicate that V1 interprets in V2. If two varieties interpret both ways, we say that they're equi-interpretable. So just some very basic examples. I just saw Miklos Marodi give a talk on interpretability because him and his co-authors have done some very deep work in the interpretability lattice. And these are some of his basic examples. So the variety of groups interprets in the variety of abelian groups. That's a quite basic interpretation. The variety of Boolean rings and Boolean algebras are equi-interpretable. The variety of sets and the variety of semigroups are surprisingly equi-interpretable. And something that will be more relevant for the remainder of this talk is we can look at a particular type of variety which just has a single ternary operation, and it's axiomatized by the Maltsev identities. And of course, because groups have a group term that satisfies the Maltsev identities, then we have that this particular variety interprets into the variety of groups. Okay, so it's a fact that the class of varieties modulo the equi-interpretability relation forms a bounded lattice. And roughly, we can think of this lattice as ordering varieties in terms of the strength of the identities that are satisfied. So it's quite natural to consider upward closed classes of subclasses of varieties in this poset if we're interested in comparing different types of sets of identities. So there's two particular type of upward closed classes that have been very important in universal algebra. The first one has come to be called a strong Maltsev condition. And a strong Maltsev condition, a class of varieties is characterized by a strong Maltsev condition if there exists a finitely presented variety. So what this means is that it has a finite signature and it's axiomatized by finitely many identities. And we just look at all of the varieties in the interpretability lattice above it. And we say that that class is characterized by the strong Maltsev condition given by whatever finitely presented variety we picked. On the other hand, many interesting classes are actually characterized by what has come to be known as a Maltsev condition. And for that, we take a countable decreasing chain of strong Maltsev conditions in the interpretability lattice. So maybe we have something that's not exactly characterized by Maltsev condition, but we do have this infinite descending chain of strong Maltsev conditions, and we call such a condition uh, uh, the class of varieties that are in this upset. We say that this is characterized by a Maltsev condition. Okay, so this is just a picture that I made. There's not much information in it. It's just something that I like to imagine. We have a picture of a general lattice here, and at the top we have the interpretability class represented by the variety of trivial one-element algebras and in some signature. And in the bottom, we have the interpretability class represented by set. And on the left here, we have just some single finitely presented variety. I probably should have put some equivalence class brackets around these varieties because these are classes in the interpretability lattice, but actually for this talk, it's not so important. Okay, so Maltsev conditions have been extensively used, so I expect that everybody in the audience knows what these are. A few classical examples. Of course, the reason that they're called Maltsev conditions is because Maltsev discovered the Maltsev term and showed that Maltsev terms characterize the class of congruence permutable varieties. Pixley showed that the class of permutable and distributive varieties is also a strong Maltsev class. So he has a term named after him, a Pixley term, which presents a strong Maltsev condition. The class of distributive varieties, it was discovered by Janssen that is definable with a Maltsev condition. And the class of modular varieties is definable with a Maltsev condition. And of course, these are famous sequences of terms. We have the Janssen terms and the Day terms. And now these are proper Maltsev conditions. And it was actually proved that they are not strong Maltsev conditions by Fitchner and Kelly. I believe independently proved that both congruence distributivity and congruence modularity are not strong Maltsev classes. And I want to point out that each of their arguments appears to be some syntactic analysis of the actual conditions, showing that we don't have some collapse in the chain of descending conditions. So we say a variety V of algebras is congruence meets semidistributive if its congruence lattices across the variety satisfy the meet semidistributive law. And here it is. I'm not going to be analyzing this law very much. And in fact, I'm going to rely on some work of others later in the talk. So we don't actually need to inspect this very much. This is a condition, but other conditions that are equivalent for a variety have been discovered. So I won't be talking about this condition from now on. Kearns and Sundre and independently Lipperini showed that the class of congruence meet semidistributive varieties is characterized by a Maltsev condition. And so it's a natural question, is this definable with a strong Maltsev condition? So that's the topic that we'll be talking about for the remainder of the talk. So let's see. We can actually talk about what it means for a class of locally finite varieties to be defined by a strong or a Maltsev condition. We just throw away every variety but the locally finite varieties. And in connection with some CSP research, Siggers showed in 2015 that actually the class of locally finite Taylor varieties is definable with a strong Maltsev condition. So what this means is that if you have a finite Taylor algebra, then it has to actually have a term operation that satisfies a specific package of 6-ary, or it was later discovered 4-ary identities that have to hold. And amazingly, Mirip-Olshak proved that the class of all Taylor varieties is definable with a strong Maltsev condition, which is now called an Olshak term. So this was very big news at the time, and it initiated a much more intense scrutiny of the question of which conditions that had become important could be characterized by strong conditions. And there's a somewhat famous paper by Kojic, Krokin, Valerian, and Willard that almost completely answers this question. So they look at these classical tame congruence omitting type omitting conditions. And so I took this table out of their paper. So here we have these different type omitting conditions. Here we have conditions that don't have anything to do with local finiteness. And they were able to give, so here's yes and yes from Siggers and Olshak. This is Taylor here on the first row. And they were able to answer no to all of the others. And this is in the case of locally finite. And of course, that lifts to the general case. If you're not definable with a strong Maltsev condition when you restrict to locally finite, then you certainly won't be definable with a strong Maltsev condition in general. On the other hand, they did find that congruence meet semi-distributive varieties are definable with a strong Maltsev condition. So it remained open whether or not, in general, congruence meet semi-distributive varieties are definable with a strong Maltsev condition. Okay, so that's the history. And now I want to talk about the connection to the universal algebra commutator and type of relation that different people have studied. So called a two-dimensional congruence, which is connected with the behavior of the commutator. So first, I'm just going to define some basic objects. Let A be an algebra. I take two congruences of the algebra, and we define the algebra of theta 1, theta 2 matrices in the following way. Well, we think of 2 squared as a square, not the ordinal 4, but it's a set of pairs. And so we look at a map, all maps from, so this is a set of indices for a relation. And now we look at those matrices which are constant on their columns, but their rows are theta 1 related, and dually constant on the rows, but the columns are theta related. And we generate a subalgebra with this. So this is some classical commutator theory. We call this the algebra of theta 1, theta 2 matrices. And we say that theta 1 term condition centralizes theta 2 if no matrix from M theta 1, theta 2 has one column which determines a pair of equal elements, while the opposite column determines a pair of unequal elements. And then the term condition commutator is the least congruence delta that one can factor A by, so that theta 1 modulo delta centralizes theta 2 modulo delta. So one has to check that this is actually well defined, but it is in fact a good definition. So we denote this delta by the term condition commutator, theta 1, theta 2. We say that a congruence is abelian if when I evaluate both arguments of the term condition commutator at alpha, we, oh no, that should be 0. My apologies. So alpha is abelian if that is 0, not alpha. That's the opposite of abelian. Okay. So Kearns and Cendre and Lipperini independently showed that the following are equivalent for a variety V. 1, the variety is congruence meet semidistributive, and 2, across the variety, for all congruences of algebras in V, the commutator is as big as it could possibly be, which in this case, if we're evaluating both arguments at gamma, we produce again gamma. And the third condition is that actually, if this is holding across a variety, we really only need to check that the second condition holds for the principal congruence of the 2 generated free algebra generated by the pair X and Y. So informally, the above theorem is stating that, well, the class of congruence meets semi-distributive varieties is just the class of varieties which have no non-trivial abelian congruences. And the condition 2 holds for a variety if and only if there are no non-abelian principal congruences, which is true if and only if this free principal congruence is neutral with respect to the commutator. So now I want to define what we could call a two-dimensional congruence. So there's some history behind this, and maybe I won't cover all of it, but I'll mention that properties of matrices in a Maltsev variety, theta 1, theta 2 matrices, well, because there's a Maltsev term, it turns out that this four-ary relation, when interpreted as a binary relation on either its rows or its columns, is a congruence. And in the Friese-McKinsey commutator book, they start with the matrices, but then they take a single horizontal transitive closure and show that in a modular variety that this is actually already vertically transitively closed as well. And quite a few of the nice properties of the commutator actually follow from this. So they call this relation delta, and they distinguish between the theta 0, theta 1, theta 2 matrices and delta theta 1, theta 2. But it turns out to be somewhat advantageous to simply enforce transitivity in both directions at the outset. So that's what we do in the sequence of definitions. So we let A be a set, and we take some relation that's coordinatized by a square. So this is what it means to be two reflexive. If I have a matrix A, B, C, D, and R, then, well, we get these four matrices are also in R. And I want to point out that if we transfer this notion of reflexivity to just a pair, then we get something weaker than reflexivity. So we get something that one might call internal reflexivity. And if we're looking at a congruence, then people begin to talk about the weak congruences of an algebra instead of the congruences. Because while the full diagonal might not be there, we have that the relation will be an equivalence relation on a subalgebra. Two symmetric, this means that we can reflect a particular matrix over the its midline, or yeah, so we can flip it around either horizontally or vertically. And two transitive if we can glue two matrices together horizontally and vertically. So we say that R is a two equivalence relation if it is two reflexive, two symmetric, and two transitive. And of course, if we're looking at an algebra, then we would say that A is a two tolerance if it is an invariant relation, two reflexive, two symmetric, and a two congruence if it is invariant, reflexive, symmetric, and transitive. So we can, of course, talk about all of the things that we talk about with congruences and subalgebras. We can talk about, for a set of squares, we can talk about the least two-dimensional congruence containing that set of an algebra. And so now we can define, my apologies again, this should be theta 1, and this should be theta 2 right here. So we refer to the two-dimensional congruence, a particular one, and this is what we take to be our delta relation. So we define delta theta 1, theta 2 to be the two-dimensional congruence generated by, well, what are the generators of the matrices? And we say that theta 1 hypercentralizes theta 2 if no matrix of delta theta 1, theta 2 has one column which determines a pair of equal elements, while the opposite column determines a pair of unequal elements. So it's just the same condition, but it's quantified over this delta instead of the matrices, and that's the only distinction. And we denote the corresponding commutator in this way. Okay, so just a little more notation. If I take some two-dimensional relation, if I put an H in front of it, then I'm just taking its horizontal relational product. So that's given by this set here. And I can also talk about the vertical relational product. So this isn't the same thing as the transitive closure. This is just a single relational product, just gluing two matrices together. And uh, if we have a two reflexive relation, then we can get away with just this relational product when we take transitive closures. So in particular, it's not hard to see that delta of theta theta is actually equal to, well, now we can compose these two operators, take a power, look at all powers bigger than or equal to zero. And so this is a particular way of producing the iterated transitive closure. The least set that is compatible contains the generators of the matrices and is a two-dimensional congruence. So in particular, we have that the matrices are contained in delta of theta theta, and it follows that the hypercommutator is always an upper bound for the term condition commutator. So we want to talk about two more theorems which are important for our characterization. One of them is a characterization for this hypercommutator, which is quite nice. So it gives an explicit description in terms of the delta relation of what elements are in the hypercommutator. But of course, there's another typo that I missed. So this should be XY. So the following are equivalent. The pair XY belong to the hypercommutator of theta theta, or we can find a square with three X's and a Y belonging to delta of theta theta. And this follows from a result of Kearns and Cendre, where they analyzed the relationship between the so-called linear commutator and the term condition commutator, the symmetric term condition commutator. They show that those are equal in a Taylor variety. So I don't want to go into all the details, but the term condition, the linear commutator rules above all of the other commutators. So because Kearns and Cendre showed that the symmetric term condition commutator is equal to the linear term condition commutator in a Taylor algebra, we certainly have that the term condition commutator is equal to the hypercommutator when they're evaluated at the same congruence in both arguments. Okay, so now what I want to do is define for a variety. I look at the two generated free algebra and a variety, and I define what we'll call the set of elementary XY matrices. It's just going to be the subalgebra of matrices generated by these specific guys. So I'm not generating a congruence. We're just generating with these specific 6 squares. And if there's a way to put together all of the previous things that we had just described, and we can obtain the following theorem. The following are equivalent. V is congruence meet semidistributive. I can find this element of delta gamma gamma with 3 X's and a Y. These are the generators of the free algebra. Or I can find in this iterated transitive closure of now these elementary XY matrices. And that's simply because it's not too hard to show that this iterated transitive closure of the elementary matrices is exactly equal to delta. And it's because if we transitively close these elementary matrices, then we're going to produce the generators of the gamma gamma matrices along the way. Okay, but condition 3, the equivalence of 1 and 3 actually allows us to produce a Maltsev condition, which at least to me seemed more amenable to analysis. So this is our Maltsev condition. And I want to explain what these pictures mean. So up here on the top left, we say that this little diagram here stands for this. So if I have a square and I put a symbol inside of it, then that just means that I've taken that operation and it's a 6-area operation in this case, and I've evaluated it at these 6 generators. Uh, so this is a particular elementary square um, with just a basic operation applied to the 6 generators. And so now we can express equalities like the ability to glue two things together with these equals signs here. So uh, this means that we can produce some diagram in a regular fashion, which one of these has to be satisfied if we're going to end up with 3x's and a y belonging to our delta relation. So the simplest one is just uh, we have some term operation that does it for a single go. Not even a matrix, but this particular set of elementary xy squares. Okay, so what can we do? Well, we remember we're taking powers of horizontal then vertical transitive closure. So if I take a horizontal transitive, I'm sorry, not transitive closure, relational product. So if I glue two squares together horizontally, take the resulting square and glue it vertically, then these are the equalities that have to be satisfied. And it might be that already I have 3x's and a y as some corner identities. And we just keep on going in this fashion. So in this case, I have 16 squares. In this case, I have, how many squares is this? 16 times 4, and so on and so forth. So um, because these are, because the elementary XY matrices for a variety are a two reflexive relation, it's also not hard to see that this is actually a Maltsev condition, meaning that it is actually a descending chain in the interpretability lattice, these equational conditions that we're presenting. Okay, so we'll denote by Vn the variety which is presented by the identities sigma n. And to show that there's no strong condition that characterizes congruence meets semidistributivity. Sorry, just one moment. Uh, well, okay, we just need to produce some congruence meets semidistributive variety that doesn't interpret Vn for each n greater than or equal to 0. So what we're going to do, so I'm claiming that the condition is not strong, so this has to be the case for actually the sigma n's. But these conditions are somewhat cumbersome to work with. So I wanted to try to find the simplest one that I could find and see that I could argue that it doesn't have sigma n terms, that I could find some condition that doesn't have sigma n terms. So we define another sequence of conditions, and given L, we take two L plus one 4-ary operation symbols. So again, by the theorem that we had earlier, this will present a SD meet variety, but now we're only looking at a single horizontal transitive closure before we obtain 3x's and a y. Um, and so we call this condition lambda L. And so now we just need to analyze terms to show that this actually works. So recall that we have this particular collection of what we're calling elementary squares, and we want to show, so this is now going to be the free algebra FL instead of FWL. I'm writing FL for the two-generated free algebra in this variety here. So I'm going to look at the two-generated free algebra, and I just want to show that for big enough L, I don't have some particular sigma n terms. So we want to show that for any n, there is going to exist an L so that it is impossible to glue together such squares to obtain a diagram witnessing the condition sigma n. So I'll just name the signature for the lambda identities. Remember, these are the S0 up to S2L plus 1. And essentially, our argument is proceeds by induction on term complexity. So we want to gradually enlarge these sets before we get all of the elementary XY matrices. So we start with E0, which is just our set of generators, and then we recursively apply our basic operation symbols. So this is just a standard way to generate a subalgebra. So our goal is to show that for large enough L, there does not exist any K where I can get this special matrix with three X's and a Y that belongs to the n-fold application of horizontal then vertical relational product of EK. And okay, so how do we do it? Well, what if we could treat subterms of terms like they were actually just free generators? So that's a naive idea, but if you just stare at the condition and you start working with the terms, one wishes that they could just treat them like they're free generators because then the analysis becomes much easier. So if we define sigma Li to be the condition produced by deleting the operation Si from the signature tau L and all identities mentioning it, then the corresponding variety has an interpretation with projections. So because of that, it would be possible to reduce the complexity of the terms of any diagram witnessing sigma n by interpreting tau Li operation symbols as projections. But this would lead to a contradiction because, well, we could reduce the term complexity of a minimal counterexample that witnesses sigma n. So this is a picture of the idea here. So up here is the condition sigma L, and let's just say that L is small. Let's say that L is 10 or something. No, let's say that L is large. Okay, L is large, but over here, N is equal to 1 because I've only taken one horizontal relational product and then a vertical relational product. Okay, so because N is 1, I can only use 4 basic term operations. I can of the coming from lambda. I can only use 4 of these symbols. So in particular, I'm not using S1. And so if I had some nice lemma that said, well, actually, you don't need any of the identities to uh, uh, you don't need any of the identities involving S1 to deduce any of these equalities. If I had a lemma that was like that, then I could interpret this uh, uh, this set of identities with projections. And then when I apply that interpretation to projections to these matrices, then in this case, with this particular interpretation by projections, all of the operations are happening over here. All the basic operations are happening over here. Those are interpreted with the first projection. Then I'm just going to pull out this red square. So maybe I'll explain what this diagram is meant to mean. This is S10, the basic operation symbol. It's a 4-area operation symbol, and I'm applying it to a red matrix, a blue matrix, a green matrix, and a black matrix, and all 4 corners here. And so these matrices are meant to come from some earlier E. Okay. So this is the idea that because we're only allowed to use a small number of basic operation symbols, if we could just forget about one of them, then we can interpret the identities that we need with projections and we can reduce the term complexity. And that produces a contradiction because we can't glue the E0 squares. We can't glue any of these squares together to get a 3 X's and a Y matrix. Okay, so to prove that the strategy actually works, we prefer to construct the free algebra recursively so that its underlying set is a collection of minimal term complexity normal forms. So I prefer to do it this way because there's some paranoia about equational logic that I have. So if I just think of the free algebra as a collection of equivalence classes of terms, then there's always some fear that I've missed something. So what we'll do is define a sequence of sets. We'll start with the generators, and we just gradually enlarge these with by applying the basic operations. And so we basically define a bunch of partial algebras. So given tau L partial algebra FLK, we define the next partial algebra just by extending it where it's not defined. And we do this by either applying some of our identities in some uh, predetermined fashion, or there's no identity to apply, and then we just call that a new term. And so in this way, we're constructing the normal forms as we go. And then we just define the universe of the free algebra to be the union, and we interpret the operations in the obvious way. So, okay, let's just see how this works at the first layer. So I start out with my set just x and y, and now this table is telling me uh, what are going to be the new things that I generate. Well, I have some identities that are going to be applied. Uh, and so in some cases, I'll just get generators back. And in other cases, I have these connecting identities. So you'll remember there was this gluing of matrices together. So always we pick the lower index uh, to pick the output of our operation. So this is S1 of XXYY, but we define the operation, we define the operation S1 interpreted in this partial algebra, the first layer, we define it to be S0 of XXYY, and that's because I have an identity that tells me that those two terms are equal. So we always pick the lower index. Okay, and then we just proceed recursively. So this is really the same table, and we only use this table when we have to. And we only use this table also when there are at most two distinct arguments, and otherwise we just have fresh terms. Okay, so there's some, I don't think it's, there's some analysis that has to be done. Okay, but here's our lemma. Let L be greater than or equal to 1, M be greater than or equal to 1, and we're going to consider a set of tau L terms of this form where I'm taking some of my normal forms from the free algebra, and now I'm applying a basic term to them. I'm sorry, a basic operation symbol. So I'm only looking at terms of this form. I have some set of them, and I'm going to let Z, capital Z, be the set of indices of these terms. And the idea is that if Z is sparse enough, and it doesn't have to be very sparse at all, but if it is sparse enough in this particular way among 2L plus 1, if the set of indices is sparse enough inside of 2L plus 1, then we can deduce equality. Well, it's not even a deduction. It's just that equality holds when this term is interpreted in the free algebra, if and only if equality holds in this now free algebra where we're treating these normal forms like they're free generators. So basically what this is saying is that if the set of indices where the set of indices for basic term operations is sparse enough inside of all indices, there's going to exist some term that I can, I'm sorry, some basic operation that I can forget about entirely. And all of the deductions that I can make can be equivalently made in this variety where I've forgotten entirely about that basic operation symbol. But this requires that these are normal forms. So that's important. Okay, so I just wanted to give some picture about why this should be true. And it's essentially because we don't have uh, long applications of transitivity when we're applying these identities. So for these connection identities, we basically can just scoot over. And even if I had all the identities at my disposal, well, I can't scoot over anymore. There's nothing more for me to do, and there's no composition laws. So actually, I had earlier been looking at a condition with ternary operation symbols that I thought would for sure work. But the problem is that actually these two scooted in here and then it broke actually. So if there was a chain of equalities here, then I would actually need all of my identities, but there is everything gets stuck. So there is no long chain of equalities. We just have some single equality and then we're stuck. So if if my set of basic term operations, for instance, if S1 belonged to it, then very optimistically, the most identities that I would need would either mention S1, I'm sorry, S2 or S0 here. Those are the only identities I need. So that means that if we're looking at some n for our sigma n condition with a small number of squares, we can obviously pick a big L, and there's going to be some big gap where we're going to be able to pick a basic term operation, and we won't need any of those identities. So to summarize the strategy, we fix n greater than or equal to 0, and we choose L so that the lemma applies. So for example, we could pick L to be bigger than 2 times 4 to the n. And we want to show that WL has no sigma n terms, and we assume to the contrary, then, well, then this is certainly true. That's just comes from our characterization of, this is just what it means to assume to the contrary. So we defined E0 and recursively the EKs in this way. And okay, so if this matrix with 3x's and a y belongs to this particular horizontal then vertical relational composition applied n times with some matrices, well, that's finitely many of these matrices. So there's going to be some minimal k, some minimal number of times that we need to generate from our E0 set, such that 3x's and a y belongs to the nth power of horizontal then vertical relational composition applied to EK. And obviously k is not equal to 0, but then we can apply this lemma and find that k minus 1 also works, which is a contradiction. So here's maybe a picture for a more detailed picture for how it would work with when n is equal to 2. So we would have these 16 matrices, and now these corner identities can be expressed in terms of idempotence. And now we can interpret all of these equalities. There's going to exist some big L where all of these equalities can actually be interpreted by projections, and that's a contradiction. So some remarks. I think that the pathway to proving this characterization of SD meet in terms of the hypercommutator and the two-dimensional congruences, there's a simpler argument. So I'm not sure if I'm going to include that in the paper or write it up separately, but there is a more direct argument. But on the other hand, I wanted to include all of the work that people have done. And then also, I believe that a similar style of argument shows that the class of varieties having a weak difference term is also not definable with a strong Maltsev condition. Okay, thank you.